All right, we'll continue this 3.9. All right, related rates. And another example of a ladder here, where we have the top of the ladder here. Let's see. Slides down a vertical wall at a rate. So yeah, here if we put these, it's going to be negative. So 0.375 meter per second at a moment when the bottom of the ladder is 6 meters from the wall. It slides away from the wall at a rate 0.5 meter per second. So that's the xdt. So here dy dt, and this is the xdt, right? And how long is, you see the question now changed. In the previous one, this ladder here is given the length, and now we're looking for how long it is. So what is that, z or l, right? But we'll do the same thing. So we will do, we know this type of problem is the z squared equal x squared plus y squared. We differentiate. Reduced by a 2. And here, let's look at something. So let's stop here. And look at it. This is where the constant thing is going to be useful to know. The x is changing with respect of time, right? Of t. The y is changing as well with respect of t. Now the question, does z change with respect of t? No. The answer is no. The length of this ladder is the same thing. It does not change. It's a fixed thing. So the z is the, here we call it the how long is it, z, it's not changing. So I did as we usually do just to show, but this problem, we're going to get stuck because dz dt is not something that's existing. Since z is constant, so now we've seen it. I didn't want to do it from the beginning, but to show, since z is constant, then the z dt is 0. That's the first thing we did with, so let's go back to this, right? So we don't have it here, but we should, here, like d of c dx is 0 with respect to that. So here, similarly, it's 0. So this left side, 0 times z is 0, and we get x dx dt plus y dy dt. And of course, the question here will be, where is z? We don't have z. If we don't have z, we can't find it. Well, it doesn't matter, because z is connected with x and y. Z squared equals x squared plus y squared. So z is the square root of x squared plus y squared. So if we find the x and y, we can find the other two. All right, so we can move to next step by solving for dy dt, and let's go ahead and divide by y. And here we're given dy, since of course, since it's coming down, and we use here the x direction, and this is the y direction, is coming down, it's going to be of course negative there. Or we can put it, now that we talk about it, it's not gonna affect much, but just for a notation there, and I'll talk a little more about it. So dy dt, let's, before we do that, so let's do 0.375. This is the y, and the x dt is given as well as 0.5. All right. Now we're missing x. X is 6. That's what we're looking for. So x is 6. So we can solve for y and get that by itself. So we didn't need to do this part here. And you see, if we didn't have that negative there, we will find here that y is negative, and we'll say, okay, that's, we needed to put that negative there to make the y positive. And this is going to be 8. All right, so we know x is 6, y is 8. So z is 6 squared plus 8 squared, and it's going to be to 10, right? $10. All right, so let's summarize again this example. We have it's sliding down, and by this rate, and the x direction is sliding this way with this rate. And so the governing equation here is x squared equal y, z squared, or the L squared equal x squared plus y squared. We kind of implicitly differentiate. Then we find out that after that, we find that dz dt is not changing here, right? So it's 0. So the left side is 0, so we get x dx dt. This is given, and we need the x and y. X is given, so it allows us to get the y. And once we get the y, right, y has to come up positive. So that's what's going to remind us, if we miss this negative there, has to come up positive. From this multiplication and division, and then the z, or the L, we can call it L if we want to, or the L is just going to be back to the basic idea of the Pythagorean theorem, and we get it. So Boyle's law states that when a sample of a gas is compressed at a constant temperature, the pressure P and volume satisfy the equation PV equals C, where C is a constant. Suppose that at a certain instant volume, the pressure is 100 kilopascal, and the pressure is increasing at a rate of, so this is the rate for the pressure, 20 kilopascal per minute. At what rate is the volume decreasing at this instant? All right. So the governing thing is given, right? PV equals C. We're given that the volume is 600 centimeter cube. We're given that the pressure is 100 kilopascal. We're given the rate for the pressure is 20 kilopascal per minute. All right, so this is what we want to differentiate. Keep in mind here, the pressure and the volume, they're both, you see here, let's go back to this, it's compressed at a constant temperature, not constant pressure, constant temperature. So both the pressure and the volume here are changing, right? So this, to differentiate here, we need a product rule, because P is not a multiple, right? So it's going to be that P dV dt plus V dP dt, and here dC dt. You see this is a constant, so it's 0. The question is about dV dt, so we will solve, get these apart. We'll divide by P. And so the pressure is all right, we're missing a negative there, because this here, P dV dt, you subtract both sides, right? You get dP dt. All right, so we need that. And now we can just go ahead and replace the 600 and 100 and a 20, right? So dV dt is negative 120 centimeter cube per minute. So again, the statement, at what rate the volume is decreasing at this instant. So the volume is decreasing at the instant that the question is about, at 120 centimeter cube per minute.